Alright, it's time to start talking about thermodynamics, and particularly thermodynamic work. You'll remember from last semester that work is equal to force times distance over which that force acts. We're not going to throw in the cosine theta here. We're just going to assume everything is lined up. So the force and the displacement are either in the same direction or at least in exactly opposite directions. So in thermodynamics, what we're mostly thinking about is expanding gases. So in particular, actually, we're thinking about pistons. So if you imagine a piston with a closed end on one side, a cylinder, okay, extend it out, and then you're going to have, here's your piston, and then this is going off someplace to do actual work. Your gas is in here, okay, and the piston gets pushed back some distance, call it delta x. I'm thinking of this as being the plus x axis. Okay. Well, what's actually causing the force here? You would ask yourself. If we're going to look for the force, the distance of displacement is actually just delta x, of course. Well, the force is actually the gas pressure pushing on it and making it move. Now, if you're being really perceptive, technically there's a pressure inside and a smaller pressure outside here somewhere. But we're only interested in the work done by the gas inside for right now. So the pressure P. Well, how much force does pressure P exert? Well, force is equal to pressure times area. So the total work must be force, that's pressure times area, times delta x. Okay? That's pretty straightforward, but it's not a great way to compute things. We've got this delta x in here, so you're going to worry about how far the piston moves, and you've also got to worry about the area of the piston. Well, it turns out not so much, because the area of this piston here times the displacement, this is a volume through which the piston slides, or if you prefer, it's the amount that the volume of the chamber increases during the work. So this is really pressure times change in volume inside that chamber. This work is equal to P delta V is the fundamental definition of work, or it's not fundamental, it's derived, but it is the important definition of work we're going to have for the purposes of thermodynamics going forward. So you always want to know what the pressure inside is and then how much the volume changes. You'll notice that the volume doesn't change at all. If you jack up the pressure a lot, but you don't change the volume, so for instance you got a sealed up Erlenmeyer flask and the stopper doesn't come out, no work is actually done by that process. You will also notice, by the way, if the pressure changes as the gas expands, which can happen, technically you're going to have to add the pressure times a small change in volume, and then the new pressure times the next small change in volume, plus this is, and so on and so forth. To do this properly, you actually need to do calculus. We're not going to do that. I'm not going to ask you to do any problems that are tricky like that, of course, but you can kind of imagine how you might maybe think a little bit about that. Okay, I will leave it off there. This is going to be an important equation, though, so this is a good one to get used to using, and it's one you're going to use a lot on the homeworks going forward. All right, see you next time.